Okay, thank you. Yeah, thank you for this opportunity and for giving me space to talk today. Okay, so I'll start thinking about this. This is a work in progress, so won't explain everything. The solution. This is my thesis project, so it's still work in progress. Okay, so I'll start by giving a little context on where do the Holstrominger, where does the Holstrominger system come from? So in the mid-80s, around the mid-80s, there was a lot of interest in string theory, and they were interested in manifolds of the type n cross m, where n was 4-dimensional and n was 6-dimensional, which this was the n was supersymmetric space-time manifold, and n was at the beginning it was a Kähler-Calabi-Yau manifold, but well, sorry. Oh, yeah, at the beginning it was a Kähler manifold, but later on, Holland-Strominger proposed a system for string theory that made and be non-Kähler. So yeah, I'll explain what is non-Kähler for n, okay, but still Calabi-Yau. So I'll explain what is the system. So the system is again m complex threefold manifold, and with non-vanishing ratio form. Okay, and yeah, of course, with a fundamental form omega. So omega is a fundamental form of the Hermitian metric, and also we have a vector bundle E and with metric H, where H is metric of E, well, at the fibers, not E, at its fibers. And yes, then the Holstrominger system is basically set of three equations. So we can write as three equations. So the first one is the Yang-Mills equations. So so f h which omega squared equal to 0, and f to 0 of f to 0 of h equals f to h equals 0. So these are the Yang-Mills. Now h, and the second one will be at least the delta bar of omega to be is alpha over 4, where alpha is just a real number of the trace of r minus h. Okay, this is called the Bianchi identity, and 3 is a conformally balanced. So that means that the metric is conformally balanced. So sine omega squared is equal to 0. So this is that is conformally balanced. So for this talk, I'm gonna mainly focus on good manifolds to do this. So I'm mainly gonna focus on I'm mainly gonna focus on the construction for a suitable n. The rest is work in progress. Okay. So well, I guess one thing I want to mention is yeah, this first equation. Well, the first equation, the Yang-Mills equations, are going to be solved if the vector bundle is a stable bundle. So this is actually Uhlenbeck-Yau theorem that is equivalent to have a solution for MUs if the bundle is stable. Okay, and well, here is now that is the term connection of omega, and this now that is a unitary connection. Sorry. Okay, so I'm gonna write some examples of solutions. So the first easy solution for this system is easy. Is the Calabi-Yau manifolds, where we take E to be the holomorphic tangent space of N, and yeah, H would be just given by omega, and this would imply first of all that omega is equal to 0, the equations, and also on the balance part. So 0, which will imply that this is Kähler and Rich flat, right? So Calabi-Yau. Now the first non-Kähler, so this is Kähler solution. The first non-Kähler solutions were given by Hu and Yau on around 2007. Okay, and they were given for as T2 torus vibrations over H3 surfaces. Okay, and later on, the same approach was expanded for more solutions, for more examples by Pino, Gansharov, and Missoni, this on 2021. And these were given again as T2 vibrations over K3 orbit surfaces with at most 9 A1 similarities. Okay. So this is the result that I'll be trying to expand. I'll state both results in one single theorem. So basically, the theorem is that we have that for that K between 13 and 22, and R between 14 and 22. So we have that S1 connected sum with S2 cross S3 and some R times of S2 cross S4 and some R plus 1 of S3 cross S3. Are these manifolds admit solutions for the post-terminal system. That is, that they have a non-vanishing one form and a complex structure, such that they allow this solutions to these systems. And the case where K is equal to 22 and R is equal to 22 is exactly the solution by Hu and Yau. Okay. Yeah. One thing I want to mention is the at least the construction by Pino, Renzo, and Bambesoni was made over well-formed complete intersections on weighted projective spaces. So actually, it was given in the intersection of 6 of degree 6 codimension 1. So intersection of 2 codimension 1 degree 6 manifolds containing the weighted projective space 2, 2, 3, 3. And well, this is a K3 surface because there's the differential formula on weighted projective spaces, which has that junction formula. It says that omega x, omega x is equal to or isomorphic to O of x, sum of the degrees minus some AI. I'm sorry, this is where x, here I'm going to write x is equal to x d1 to dk, and it's containing the mean of a1, no, a0 to an. So, and actually, Miles Reed found a list of 95 K3 surfaces of surfaces of codimension 1 of weighted projective spaces, and then Jan Fletcher found more examples of over higher codimension. And actually, this is one of the surfaces in Jan Fletcher's list, and it's what they use. And actually, this surface has 9 A1 singularities. And well, the surface that I'm going to work on is actually X30 contained in P. I think let me just recheck. So this is contained in. Sorry, this is here 5, 6, 8, and 11, and it has one A1 singularity, and a 7 singularity, and an 8 singularity. Okay, so the methods by Pino, Rancher, and Besoni only take care of singularities of A1 type. I'll explain what is an AN singularity actually now. So, well, in general, an AN singularity, there's many ways to characterize this. It's a dual singularity. So, actually, this AN singularity is in a surface complex surface X is let's say it's at the point P of X, such that we have a neighborhood W of X where P is containing X. No, sorry, W, such that W is isomorphic to let's say it's some call plus 1, and let's say U, this description, let's say it's analytic, so U is a ball, a complex ball in C2 containing the origin. And the action of this group is by multiplying by the group n plus 1 group of unity. So, if n is 1 units of unity. Okay. Okay. So Okay, now the method that we're going to use is resolving these singularities and getting more manifolds, so or repos. Oh yeah, also I'll explain what's in order. In general, what is this space? So, yeah, also we'll say X is orbital surface, complex orbital surface, complex orbital surface, where say sigma is its set of points P1 Pk are singular points. So singular points. So we'll consider the surfaces with singular points. Yeah, we'll even talk about K surfaces. We need a notion of a canonical bundle. So the definition will be omega n of x will be defined as the push forward of the inclusion of x minus sigma, where is the points. I mean, this will be smooth, so this is well defined. So this shift will be defined as as I said, the push forward of this other shift. Okay. Now, now I'll talk about how the blow-ups look of these singular points. So a little description. Oh, and another way there's several ways to characterize these singularities. But yeah, another way to describe them is that W is symmetric to the variety generated by xy plus n plus 1. So this is, you can see, for example, when n is equal to 1, this would be like a cone. So yeah, this is the type of singularities that we're dealing with. And
it's more or less like reversing on elliptic vibrations.
Yeah. We'll get to that. It's in the end we'll use cipher bundles, and it will be T2 vibrations. Yeah.
So cipher bundles.
Yes, I'll use the cipher bundles. Yeah.
This is the regular part. So probably this shift depends on bundle.
Yeah. Okay. I mean, yeah, this is the canonical shift. But yeah, to be K3, of course, this omega n has to be isomorphic to 1 over x, right? Okay. So I'll this is basic for the rectangular. So I'll look at resolutions of these singularities via blow-ups, and I'll show how it looks more or less. So in the case of so let's consider the blow-up W tilde for now. Let's consider with the coordinates x, y, z, u, v, w. I'm saying w plus 2. So yeah, this I will consider some neighborhoods. So let's say the neighborhood when w is non-zero. The equation for after the blow-up will be u over w times v over w plus c n minus 1. When v is non-zero, we have u over v plus w over v squared z n minus 1. And u is non-zero is v over u plus w over u z n minus 1. Okay. So yeah, in the case when we have n equals 1, this will become, well, the exceptional divisor will be this tonic. So just one connected component, and the case when n is greater than 1, the exceptional divisor will be given by two curves by two lengths. Okay. Now, right, for the case n let's say this is the class of the exceptional divisor, so this will be non-conditional right as p and p prime. And in the other case, just p. Okay. So this is now for the cipher bundles, we need to know the divisors and in order to construct them. I mean, the properties of the cipher bundles come to like knowing what, like working with the divisors themselves. Okay, and actually smoothness and simply connectedness depend on right choices of divisors for this. Okay, so we have to know what are these divisors, and actually one thing has to mention is that Del Castro in her thesis showed that every K3 services in mouse read list is generated by just the hyperplane section. So, I mean, in a sense, all the divisors that will come up from these blowups. Okay, so we know every divisor. Okay, so I'll say let's describe the groups. Well, so that's fine. Like still next be just a blowup of one singularity, and let's say it's an AN singularity. It would have to be bigger than 1, because in the A1 case, it's easy. It's just going to be the one generated by the exceptional divisor. It's just going to be the hyperplane section and the divisor generated by this exceptional divisor. In the other case, the generators are a little bit more tricky, but not so much. So let's say, okay, so I have that the Picard group of X tilde is going to be in the Picard group of X plus G2, where actually this can write it right away. So, yeah, let's say this is generated by the divisor generated by the divisor generated by the VLU, or yeah, sorry, the line bundle generated by the VLU, and the exceptional divisor. So I guess already like this for now. Okay. So yeah, these are the two generators, and actually this there's one property of these Orbi surfaces is that they're Q-card here. So which means that every divisor or every line bundle here will be generated by a multiple of Bay divisors. Okay, so that's that gives me that assures me that we'll know what are these right here, because the Bay divisors will clearly just be the divisors that are in the surface X plus the divisors that well, just these two curves, right? But in these the curves by themselves, they don't generate a line bundle because they're generated by two equations. Okay, so actually, let me just say here that U tilde would be actually n minus 1 e plus 2 times the hyperplane section. And yeah, this the other divisor is just the sum of the components, and I'll show a little bit why this is true. So since we know that this is Q-card here, I know that for any L in the Picard next filter, and L is going to be N times alpha E plus delta E prime. Okay, and then I mean I could have some hyperplane, but I can just multiply by the inverse and well I have the inverse and get it to this form. Now yeah, this we can just now kind of subtract n beta n beta times the exceptional divisor. So it's right e plus e, right? And on both sides, so I get this is n alpha minus beta equal e. Okay. Now I computed the intersections of divisors with the exceptional divisor components. So one thing I know is that u tilde that e is going to be just one. So it's yeah, it's like I mean an example for it is in the card form, for example, that when n is equal to 2. So yeah, when n is equal to 2, this is in the end it will be this implies that e prime that's sorry, this is e prime is 1 over n minus 1. Okay. But yeah, so if I intersect both sides by e prime, I will get of course an integer here. When I'm intersecting a Cartier by a ray divisor, so I get an integer. It's L minus n prime is equal to this n alpha minus beta e dot prime. So since this is n minus 1, that means that this is n minus 1 over n minus 1. This means that this 1 over n minus 1 divides this side, so that would imply that actually sorry, this is a multiple, let's say k of u tilde. So it shows that every divisor here or every line then bundle here will be generated by these two guys. Okay. Now the cipher bundle that we're going to use there's a more general constructions, well, more general cipher bundles, but in our case, the cipher bundle that we're going to use is actually this will be a C kind of C star bundle, but you can contract the C star to make it S1 bundle. But yeah, these type of bundles will be defined as Y the spec of okay, so this is the construction for the cipher bundles generated by of course L in the Picard X. Okay. Now yeah, now next yeah, also we define the first term class of Y functions. Next is by definition will be just the divisor L. Although we can they usually write as a ray divisor, or in our case it's the same. So it's fine. Yeah. Now, a few propositions by Color. Color found that so this is by Color. Yeah. So y. So y is smooth along the fingers of x, where of course f is this function, this projection. If and only if C1 y(x) is generator of the local cluster V of x and x. So in the case of the singular points, this will be just z over minus one. Yeah, that's right. And yeah, this I want to mention that we can choose some combination where, for example, the case where we had the AN. Well, in our case, we had A1, A7, and A10. So if we use as a part or the exceptional divisor, we will always generate here in the case of A10, right? Because when we blow up, well, A10 will have Z over 11, for example, or at least actually n minus 1 instead of blow up. So we'll have a Z over 9, and it's even. So the exceptional divisor will have like 2, so it will generate this group. It's fine. And now this is smoothness. Now another proposition. Well, another proposition by Color means that it says that yeah. I mean, we can show actually that just that we can choose the right divisors in order to have the first homology to be 0, or for it to be simply connected. Okay. Now, when the last thing it's here. And so this is the last part. So again, it's x 30 5 and as I said, which has A1, A7, and A10 singularities. Then for every k, so whatever k between 2 and 18, we can find 2 divisors. Let's say it's in student. And 1 plus and 1 plus. Positive 1 plus and later, such that 1 V2 of x tilde is x is k. 2 intersection of B and omega is equal to the intersection of B and omega is equal to 0. So they're primitive. And 3, decipher this one bundle. Decipher this one bundles y tilde x tilde determines. So this is determined by C1 y x and find y to the two, y to the one, then by C1 to 1, 2, then pull back. Yeah, C prime are smooth, and simply connected. Okay, that would yeah, these are prospects. This well, why for every chaos there will be one white